Good afternoon, ladies and gentlemen. Welcome to another in our series of lunchtime lectures. The July lecture series is sponsored by TerraCore Geospectral Imaging, and we're very pleased to have today with us Alan Jones, who is probably the world's foremost expert in magnetotellurics.
What do you mean, probably?
Okay, he is. He is.
Sorry.
I noticed that Alan's first slide is something entitled, "Who Am I?" So I don't have to do too much of an introduction, but I think a lot of you know who he is anyway. Just as he's got his first degree was in physics, and we won't hold that against him.
No.
From the University of Nottingham. He did an MSc in Applied Geophysics at the University of Birmingham. He did his PhD in geophysics at the University of Edinburgh and received that in 1977. He has a whole history of moving around to various places, from Münster University in Germany, Geological Survey of Sweden, University of Toronto, Geological Survey of Canada and divisions therein, and has been involved in a number of lithoprobe programs around the world over the years, including some in South Africa. He is currently Senior Professor Emeritus at the Dublin Institute for Advanced Studies, and he's also holding positions at the China University of Geosciences, Macquarie University, and the University of Western Australia. And he retired, I guess, 2 or 3 years ago, and on retirement, he formed a Magnetotellurics consulting company, Complete MT Solutions, with former students and a colleague in 2016. There's a long series of awards that he's received, and he's published almost 200 papers. I think most of us who are mere geologists recognize Alan for his cooperation with the great unwashed in the field. And with that, I'll let Alan take it away. So Alan, go ahead.
Well, thanks very much, Craig, and thank you for the invitation to give this webinar, and thank you everybody who's taking the time to listen, and I just hope I deserve your time. So what I'd like to do is give you an introduction to magnetotellurics, and particularly with a focus on mining. And this might be a little bit different from what you might be expecting, because I'm gonna stand back and look at the big picture first, and then zoom in and get smaller and smaller. So oh, there we are. So Craig just told you most of this. I'm from Manchester for my sins. Got out of there as soon as I could. And then as Craig just said, I took a retirement, and in order to form a company, we have in Canada professional accreditation, and so I had to become a professional geoscientist, and so I can actually sign off on all the reports. And I've done a number of things over my life, but and I'm not saying this because I'm talking to a primarily South African audience, but I do believe that my greatest contribution to science, my greatest scientific achievement, was organizing and executing the SAMTEC South African MT experiment some years ago, which I think has been tremendous and is still able to give a lot of information. And I do think that magnetotellurics can add significantly to geoscience knowledge in a number of different ways. I mean, we're looking today at mining, but you can use it for geothermal or groundwater or all sorts of things. So I normally give a 5-day short course, and I don't know how much time you've got. or you could do a 2-year master's with me, or you could. And I've got 45 minutes for this webinar, so not a lot of time. So hang on to your hats. When I give seminars, I like to be very interactive with the audience, and particularly most geophysicists like myself, we can lapse into jargon, and we don't mean to. We lapse into jargon. So for me, I like to take visual clues from people's faces whether I'm getting my message through or not. And this is quite hard. It's quite impossible. So every now and then I'll glance up at this little window I've got that tells me questions. So if I'm not explaining something, please send a question and I'll try to explain it on the fly. So what is magnetotellurics? And most of you may be familiar with it already, some may not, but it's a natural source electromagnetic geophysical technique for obtaining models of the electrical resistivity structure below a survey area. And that's it in a nutshell. The history of it's interesting. I mean, it was forerunners of it were discussed by the Japanese in 1930s, led by Rikitake, and then Tikhonov of the regularization fame, Tikhonov regularization. He wrote a paper in 1950 that set just a very short paper in Russian that set the fundamentals of the relationship between the electric and magnetic fields. But it was a seismologist working for a company General de Geophysique in 1953 who published this absolutely wonderful paper. And you should try to read it if you can, because it's very accessible. And his focus, of course, is on sedimentary basins because he's working for an oil company. But he laid out, he gave the technique the name, he laid out the basic theory, and it's a very practical paper. And so Louis Quénard should be recognized as the father of magnetotellurics. Now, there's a number of flavors of it, going from the top level, shallowest to deepest. And at the very shallowest level, we've got a hybrid technique called radio magnetotellurics that uses VLF radio transmitters. And this is for environmental geophysics or engineering geophysics. But the type of magnetotellurics of interest to you today are these other ones, audio magnetotellurics. And it's called that because it's in the audio hearing range of 10 kilohertz to 8 hertz. And these, the energy for this is generated by lightning storms, and I'll show you this. And then that's typically looking, depending on where you are, is typically looking 3, 4, 5 kilometers. And you want station spacing to be between 50 and 500 meters, depending on your target. And you need about an hour of data, and you need to do it at night. And then we have broadband magnetotellurics, which is around 400 hertz, or around 1 millihertz or 1,000 seconds. And this uses lightning sources at high frequencies and solar wind at low frequencies. And here your stations are now further apart, maybe 1 to 10 kilometers, and you need 2 nights, 1 to 2 nights of acquisition. And then we have, when we're looking deeper into the mantle, and we have long period magnetotellurics, where we're looking down a few hundred kilometers. And there we have a month of acquisition. And in fact, there's one more form, which is very deep magnetotellurics, which I did some years ago, where we had the 1 year deployment, and we looked down 1,300 kilometers. And so the same mathematics, the same processing, the same everything can do all of these. The only difference is the magnetic sensors that you have to use. And so it is an electromagnetic geophysical technique for obtaining models of the resistivity. All electromagnetic geophysical methods sense electrical resistivity or its inverse conductivity. And one important point here is that what you get back from using magnetotellurics and any EM method generally, or potential field methods, you get models of the subsurface. Sometimes we call them images. They're not images, they're formally a model. We're getting a model, we're deriving a model that fits our data. And these are not images that you get with, say, seismic reflection. And so we're sensing electrical resistivity. And electrical resistivity of rocks is the one physical parameter that varies by more orders of magnitude than any other measurable physical parameter. And you can see here, I don't know if you can see my mouse moving, but we're going from very high resistivity on the shield, 100,000 and higher ohmmeters resistivity on shield rocks on the Yilgarn Craton, to very, very low values in massive sulfides. And I'm working with a client right now where we're seeing layers of 10 to the -4, so 2 more orders of magnitude to the left, massive sulfides. The one important point, and this is true of all geophysical techniques, is that none of our data is unique. None of our results are unique. So we get resistivity, but as you can see, the resistivity can be a number of different rock types. So we need other information. And in the context of what we're discussing today, for mining, primarily if you're looking for sulfides, then you can see that you're looking for something that's 6 orders of magnitude different. So you're looking, you're looking for a very, it's going to be small, it's relatively small, but it's hugely responsive. So it's perfect for electromagnetic methods. So very quickly, just on the sources, it's a natural source, and we have 2 sources. We have AMT source fields, and these are high frequencies, so they're only penetrating very shallowly. And these are due to worldwide thunderstorm activity. And here you can see a thunderstorm. And in the thunderstorm, the lightning that you see, about 5% of the energy goes down from the lightning to the ground, and the other 95% goes up and hits the ionosphere, and then it radiates around the world in this waveguide. And the fundamental frequency is given by this waveguide height and is around 8 Hertz. And here's a nice plot of increase in frequency, and you can see it's called the Schumann resonance after Schumann, who found it. And you can see the Schumann resonance and its harmonics. One very important point, though, is that as this signal is traveling around the world from wherever the thunderstorm might be, if it's a daytime path, then the energy gets attenuated very strongly because the Earth's atmosphere is ionized during daytime. And so the electrical conductivity of the atmosphere is 2 to 3 orders of magnitude more conducting, which means it attenuates the electromagnetic fields. So we get a lot of attenuation for daytime paths. So you really need to record at night, especially in what we call the dead band, the low signal band between 5 kilohertz and 1 kilohertz. And then at the low frequencies, which is the stuff that's penetrating deeper, what that energy comes from is the interaction between the sun and the Earth's magnetosphere. Fortunately, we have a magnetic pole. Otherwise, if the Earth didn't have a magnetic field, we wouldn't be here because we couldn't withstand all this solar ionization. And there's a dead band in this one too because of the crossover between the high frequency and low frequency. So this is a typical frequency plot, and here you can see these 2 dead bands that you have to do special things in, and that's something we can, you know, when you get into the details of acquisition, you have to worry about. So what's the theory of it? This is the theory. The theory, classical electromagnetic theory, culminated with these 4 equations, which were written down by James Clerk Maxwell, a Scotsman, who, unfortunately, his friends when he was a kid called him Dafty, but when he put together these equations and he realized particularly this term here, which is called the Maxwell term, Albert Einstein considered Maxwell's work to be the most profound change in the conception of reality since Newton. So a wonderful man. And I thought about spending the next 30 minutes going in detail over these physics equations. But then I thought, no, not going to do that. I think I've probably lost half of you already. But if any of you want to look at this, there's a wonderful website called maxwellsequations.com that really explains these equations in layman's terms. There's 2 physics phenomena that I'd like to explain, because if you get these, you really get magnetotellurics. And one is skin depth and the other is Ohm's law. Now, skin depth, the idea with skin depth is that if you have an electromagnetic field, as it propagates into the Earth, it gets attenuated, its signal gets cut. And here you've got this wonderful GIF from Martin Unsworth. This shows these blue lines going down at 2 different frequencies. This is 40 Hertz, and this one is on the left is 10 Hertz. most of the energy is radiated back up. That's the red radiation up, but some penetrates into the ground. And you can see the 40 Hertz one is going 4 times faster than the 10 Hertz one. But you can also see the 40 Hertz one doesn't go as deeply as a 10 Hertz one. And the depth of penetration, where we go to 37% of the surface value, is given roughly by this equation. 500 times the resistivity of the medium divided by the frequency you're interested in. Excuse me. And this is known as a skin depth phenomenon. And you know about skin depth, even though you might not realize you do. And that's because you know that infrared light, if you want to get warm, you sit under an infrared light, and the energy from the infrared light, because its long wavelength goes from a micrometer to a millimeter, it penetrates deep into your body and warms you up. On the other end of the spectrum, of course, is ultraviolet light. And this, of course, you know to avoid. This is very short wavelength, and so it doesn't penetrate very deeply. And here you can see the depth of penetration of UVA and UVB. We don't get UVC at the surface of the Earth, fortunately, because it's trapped in the atmosphere. Although UVC is the light you need to use to kill COVID. Just an aside there. So putting things outside in the sunlight, doesn't do the best. But you can see how what happens here is that the energy that's lost is lost in a very small distance. And so that disrupts your cells. And so that's what's damaging your cells. And this is why it's called skin depth. And here's a schematic to show the basics of magnetotellurics. Here we have it short periods or high frequencies. We always plot with increasing period to the right or decreasing frequency, because that's our proxy for depth. Here we have it low, short periods, high frequencies. The energy doesn't penetrate very deep in this 2-layer case, so we get, when we scale the numbers we get the resistivity of the top layer. And then as we go to longer and longer periods or lower and lower frequency, the energy goes deeper and deeper into the ground, and eventually it doesn't see this layer. And you can see it asymptotically approaches the resistivity of the second layer. So this is the basic principle of 1D, if you like, MT with a skin depth. And here's some theoretical curves, and you can see that we get our electric and magnetic fields and create this ratio, and that gives us this thing called apparent resistivity. And here I've got two layer cases, layer 1 over a conductor, layer 2 over a resistor. And our apparent resistivity curves, here's layer 1 going down to 3 ohms, and here's over the resistor going up to 30,000 ohms. So these are our apparent resistivity curves. We also have what we call the phase. It's how much the electric field is ahead of the magnetic field. And here we have these phase relationships, but we won't bother too much with phase in this in this presentation. The other physics phenomenon that we need in MT is called Ohm's law, and this came from Georg Simon Ohm, and he pointed out that when electric current crosses a boundary, it must be the same on either side. So here you have a fault, and you've got an electric current crossing this boundary, and it stays the same. The amplitude is the same. Now, electric current is given by electrical conductivity times electric field. So electric current must be the same on either side of this boundary, but conductivity is changing. And what that means is the electric field must change. Conductivity is much higher on this side, so the electric field is small. Conductivity is much lower on that side, and the electric field's large. And the way this happens is you get charges on this boundary. And what this means is that the magnetotellurics is very sensitive to these charges. And here we have a schematic of a fault. And there's two situations on this fault. You've got either current traveling along the fault, or you've got current traveling across the fault. And the Current traveling along the fault is what we call the TE mode. Sorry, jargon, but it's current traveling along the fault, and that's this red one. It goes smoothly from the resistivity on one side to the resistivity on the other side. But current crossing the fault has got this discontinuity because the electric fields must be discontinuous. And you can see that we've got very high sensitivity to that boundary because of this discontinuity. So onto equipment, and this is a photograph of the equipment I use for my PhD, some home-built equipment from the University of Edinburgh, and this is my supervisor, Rosemary Hutton, and Dennis Rooney, who used equipment first. He took it down to Africa, actually, to Kenya, and then he brought it back, and I had to repair it and did my work in Scotland. And the equipment printed the data out on paper charts, and I had to hand digitize the paper charts. And so here we have 5 fields. The ones at the bottom are the electric fields. North is the EX, east is EY. And then here's the magnetic fields, the HX magnetic field, HY magnetic field, and HZ varying in time. And you can see in these 2 intervals the correlation in the shape of these time series. So this is 2,500 seconds, so 40 minutes or so time series. And you can see these undulations, they occur in all of these. So the magnetic field is inducing the electric field. And I spent days and days and days and days as a student looking at these things, looking at them and trying to understand them. And you learn a lot. Well, this is modern equipment, very portable. You can get 4 systems in a smallish helicopter, quick to install, low power, 32-bit, time sync with GPS, power line noise rejection in the receiver. I think it's absolutely wonderful, but the one thing I've noticed is that the kids, as I call them, that's anyone younger than me really, they don't look at data anymore. They don't look at the time series. So here's how we install an MT system. It's very low impact compared to, we don't blow anything up. We don't need a generator to generate our electricity because it's all done for us by nature. So we put out these sensors, which we call electrodes, about 100 meters apart. And that gets us the electric field. And then we put out these magnetic coils, as they're called, to give us our magnetic field, and we record it, and then we come back a few hours or a few days later and pick it all up. So very low impact on the ground, so it's easy to do in some areas that might be sensitive. And then we have to calculate our apparent resistivities from our electric field in the frequency domain divided by a magnetic field in the frequency domain. So we're taking our time series and we're calculating using a processing code our apparent resistivities. And this is a plot from a paper I presented some years ago where 8 different people, I sent the same data to 8 different people, and I got back 8 different versions of the apparent resistivities because there's different ways of doing that transformation. And you can see that these 3 methods down here that used what's called robust statistics were by far the best, and all these non-robust methods were pretty poor. And this robust method is on the right here, is my colleague Alan Chave, who works in the company. And this robust method here is the one that's inside the Phoenix processing code, because I gave Phoenix, it's my code, and I gave Phoenix my code in the late 80s. And so once we have those apparent resistivities, what we do now is model them to get a model of the Earth. And we do that in various dimensions. So we can do it in 1D. That means you've just got it varying with depth. And here's a 1D model, except this is an unusual 1D model because it's anisotropic. We're allowing the resistivity to be different in different directions. And some of the clients that we have is finding these anisotropic models extremely useful. And then we can do it in 2 dimensions, where we assume that conductivity doesn't vary along strike. We can do it in 3 dimensions. And the examples I picked out are examples from Southern Africa. They're actually from the Samtex experiment in northern Botswana. And these 2D and 3D models were part of the thesis work of one of my best students, a guy called David Kosa, who now will be giving a talk on Friday, I noticed. One thing I want to talk about, though, is mineral system mapping. And this mineral system paradigm is the idea that you don't run around trying to find small ore bodies. What you do is try to understand the tectonic context. And so you look first on the craton scale, and this is the Yilgarn Craton in Western Australia. You look first on the craton scale, and then you go down into the camp scale. And once you're in the camp scale, you can focus in at the deposit scale and then at the ore shoot scale. And this concept of looking first regionally and going down from regional to deposit to camp to ore shoot. Cam McQuaig in Perth, one of the ones that proposed, was the strong proponent of this. And of course, the concept behind all this is that ore bodies don't occur at random places. Their emplacement is a function of tectonics. And so know the tectonic history of an area, and you're going to know where to look for mineralized bodies. And as Cam discussed, what we have is a primary source region that's at the regional scale, deep in the mantle. And this brings in a fluid reservoir from fluid delivery pathway. And the fluid reservoir, which is going to be in the mid-crust, say, you're going to get fluid flow and precipitation. That'll give you deposits. And all, and I mean all, world-class mineral deposits lie above geochemical and geophysical anomalies in the lower crust and the lithospheric mantle. So if you want to look for a large world-class scale deposit, you look for those large anomalies and then image the smaller fluid pathways. And Graham Begg, also of Perth, who's been pushing this concept of looking big first, he produced this very nice graphic that showed the type of geophysics that you have to apply as you go from the regional scale to the detection scale. And here you can see these types of broad scale methods, seismic tomography, MT, long period MT, epicenters of seismic epicenters. And then you go to broadband MT and magnetics and reflection. And then at detection scale, you would use 3D seismics, gravity, AMT, EM, IP. And the point here is to be efficient and effective. You map at the regional scale for anomaly detection, the camp scale for more precise detection, and then you go into the deposit scale to define your anomaly. And magnetotellurics has got a role in all 3 of these. We can use the long period magnetotellurics at the regional scale, broadband magnetotellurics to give the camp scale, and audio magnetotellurics to give us a deposit scale. And we know for orogenesis, there's 4 factors at play: the fertility, favorable whole lithospheric architecture, favorable transient geodynamics, and preservation, of course. And that gets us orogenesis, and we've got to preserve it. And right now, this discussion, this talk is going to be looking at architecture. You know, magnetotellurics doesn't do anything about past history or fertility or preservation. We're looking at architecture. So Australians, I'm going to show you a few examples from Australia, because the Australians have really taken magnetotellurics on as their method of choice, their tool of choice for mineral systems mapping on the large scale. And they've got a a national program called OSLAM. And why are they using MT? Well, very high sensitivity to the presence of conductors, orders of magnitude difference between the host and the conductive mineral systems. Magnetotellurics can map lithospheric structures quickly and cheaply. You need to deploy a long period MT system for a month, whereas a teleseismic system might need a year or 2 years to get information to the LAB, for example. And you then infill using broadband equipment a couple of nights, and then you infill further and delineate using AMT system. And so this is the Australian OSLAM program, and the greens have been recorded to date, over 1,000 sites, and the reds are being acquired. Oh, sorry, the reds are acquired and the greens are being acquired, wrong way around. And then they have a plan to acquire all the rest. And one thing that's super important is that all of this is publicly available right away. It's just like the US array. And so a number of different workers around the globe are taking the opportunity to jump on top of this Australian data. I'll show you some examples from that now. But when you're doing this mineral system mapping, this large scale approach, what you want to do is one of two things. You're either going to be doing domain mapping, where you, because most mineral deposits lie on the edges of domains, or you're going to do direct mapping of potential fluid pathways from the mantle into the crust. And here's a diagram from the Macquarie Group, Bill Griffiths, Sue O'Reilly, showing the Colorado Plateau, Wyoming Craton. And all of the deposits, the major deposits, lie on the edges of these domains. This is a seismic tomography map at 90 kilometers. And you can just see how they concentrate in the low velocity regions and on boundaries. So on to some examples now. This is some OSLAM work in Curnamona province, just to the east of the Gawler Craton, down here in South Australia. And they define using these this regional basis. These sites are nominally half a degree apart, so about 55 kilometers apart. They found this anomalies at two different depths, 10 kilometers and 20 kilometers. And so once they found this anomaly, they go in deeper. And here's the model from the long pier systems, where you got very few sites, a site here and a site there. And then they go in with a broadband and do a sites every few kilometers. And you can see that they've got much better definition now of these anomalies. And look at these features here. Just look at these flow through features. And this one, in fact, is the Curnamona deposit. And there's obviously a deposit or something here. Of course, the problem with Australia is you've got 200 meters of stuff on top of your bedrock that you've got to look through, and that's why magnetotellurics is really taken off in MT, is because they've got to use geophysics, and MT is a fabulous tool for looking through the cover. And here you can see exactly these fluid reservoir regions and these deposit scale bodies coming through. Perhaps the most presented MT figure over the last few years is this one from Graham Heinzen of the Adelaide Group, where they did work over Olympic Dam. They did the long period work, which showed a very fuzzy image, and then they went back and did broadband. And here you can see this wonderful image where you have this fluid reservoir, and then you have these fingers going up. One of the fingers goes up to Olympic Dam, of course, one of the world's famous IOGC deposits. One up to a couple of other deposits that were known but not economic, were Well and Vulcan, and then a fourth one that still needs to be explored. And this was called the Fingers of God, nicknamed the Fingers of God. I'm not sure who by. But these fingers exist everywhere when you start to look for them. Here we are now looking in the Yilgarn Craton and work by Mike Dentith, showing disruptions in the crust with low resistivity fingers going all the way up, and at a number of these. Here we have the Eastern Goldfields. Here we have a greenstone belt. At a number of these, there are known deposits. In Canada, I looked through the Canadian database and I don't see anything as strong as the fingers of God, but one work I did some years ago was over the Yellowknife Fault. This is in northern Canada. Here's the town of Yellowknife, and the town exists because of the Yellowknife Fault with gold in pyrite. And I found this, I don't have the fingers of God, but I've got the finger of God. So here's a finger coming straight up from something low resistivity, anomaly in the mantle, right up to the Yellowknife Fault zone. And then in Africa, of course, here's our model from Rob Evans of the Samtex main north, east, southwest profile, and of course the Bushveld. My God, that's the fist of God. I mean, that's a huge thing coming right up. But also note as well, we have a finger coming right up where Kimberley is. Oops. And so you can see that this disruption, lithospheric scale disruption in the resistivity that points right up to the Kimberley area. And so when we do domain mapping again now, here's an image. This isn't a model now. This is an image of the resistivity. I've taken the data and played with it to get an approximate depth. And this is at a depth of 200 kilometers. And the dark reds are dark blues are resistive regions. And you can see the Capval Craton here. And here you can see an outline of the Angola Craton and a little bit of the Zim Craton. And in red are diamondiferous kimberlites. And they quite clearly lie on the edges of these resistive domains, whereas the greens are away from the edges of resistive domains. So now finally on to deposit scale imaging. I love magnetotellurics. I've lived it all my life, but I'm not going to sell it to you unless it's the appropriate technique to be used for your problem, because there are other techniques. And here's an example of, on the left, we have magnetotelluric methods and their frequencies. And on the right, we have some examples of other control source electromagnetic methods. And they can go a few hundred meters as well. So control source and electromagnetic methods, if appropriate, have the advantages that they control the source, so you don't have to wait through the night for the energy to come in. You don't have to worry about dead bands. And also you can optimally design the source receiver configuration to energize your deposit. And at least in Canada, AMT really became a major geophysical tool from about the mid-1990s on, when the companies wanted to look deeper than they had been looking. And conventionally, they'd looked to about 500 meters, but then they wanted to look deeper than that. And some years ago, one of the oil company executives told me that they wanted to find ore where the church bells ring. And by that, they meant they wanted to find deeper ore where they already had the infrastructure in place. So they didn't want to go and find ore in the middle of nowhere, because it costs a lot of money to put infrastructure in place, but they wanted to find deeper ore close to existing infrastructure. And so below about 500 meters or so, it becomes logistically very expensive to use a large controlled source EM system. You've got to have large loops. You've got to put in very low frequencies, so you're going to get a lot of loss in the loop. You're going to have a number of people around to get the loop going. I did an experiment some years ago where I had a 6 kilometer long line dipole to put in energy, and I had to have 3 people, one at the transmitter and one at each end, because we were putting 30 kilowatts in the ground, and I didn't want anyone coming near those electrodes because it would have been dangerous. And in fact, the results I got were no better than the natural source AMT results I got after all. So magnetotellurics has been used to map many base and precious metals. And also in the regional context for diamond exploration. I just see someone's thrown a question. Is the MT technique more beneficial for greenfields exploration compared to brownfields exploration? That's an excellent question. I would have to say brownfields exploration can be difficult because of the electrical infrastructure that can cause a lot of noise, so it might make it difficult. And so on balance, certainly greenfields exploration is the way to go, but there have been cases where you can work close to existing infrastructure and you can take the appropriate processing methods to get rid of the noise, and so you can extend your brownfields knowledge. So here's a very, very, very incomplete list. This is just some of the work I know about. Unfortunately, there's an awful lot more work done than this, and a lot of it is confidential. I know some of it. I know it's one of those things, you know what you know, and sometimes you know what you don't know, and you don't know what you do. Yeah. So Voices Bay, in terms of nickel, Voices Bay, Sudbury, Thompson, Raglan, Griffiths, Norilsk, copper, Kidd Creek deposit. These are Canadian biased, of course. Gold, Nico deposit, BC, Carlin Trend, uranium, the Athabasca Basin, the Nico deposit, diamonds for kimberlite pipe imaging, and then also diamonds for regional studies. Unfortunately, what I can't show you, my company's been in existence for 4 years now, and we have only worked for clients who want their results to remain confidential. So I can't show you any of the work we've been doing, but I've contacted some people I know in the industry who've been very kind and given me some of their slides. And so, of course, when you're looking at something like a porphyry deposit, what you want to know is how sensitive your measurements are. And here on the right, you've got a very nice plot that shows you the change in the resistivity of the rock with the amount of sulfide in the rock. And so here on the left at the top, we have the disseminated sulfides. So some of these disseminated sulfides can become quite resistive because the sulfides, the pyrite grains, may not be connected. And then when they're in veins, they start to become more conducting. And then when you've got continuous veins, they become very conducting. And this is another point about electrical methods is, excuse me, we're sensitive to the interconnectivity. We have to have, it doesn't have to be 100% connected, but we have to have good interconnectivity. So if you look at, for example, in the Athabasca Basin for uranium exploration in the 1960s and 70s, they used gamma ray methods to get down a couple of 100 meters. And on the scale here is not linear, it's logarithmic. So they went down a few 100 meters already with gamma ray methods, about 200 meters. But then in the 80s and 90s, in order to see deeper, they used control source, active source, electromagnetic methods. And they found these deposits, Cigar Lake, Phoenix. But then to go deeper than that, to go down beyond about 500, 600 meters, in the 2000s, they've been covering the whole of the Athabasca Basin with magnetotellurics, and a huge amount of work has been done in the Athabasca Basin using MT methods. So Voices Bay, just very quickly show you this is a contour map of the phase to 100 hertz, and here you can see a very large 40-degree change. I'll show you the data in a minute. And the problem with Voices Bay, you've got C nearby, so you've got to correct for that. But here's some data. And And the one thing I want you to look at is this blob here, this orange blob. This is a very, very high phase, and that's due to an anomaly that, when interpreted, is this Eastern Deeps. So that found the Voisey's Bay deposit from airborne EM work. They were actually looking for kimberlites, and they thought the instrument was malfunctioning because they weren't getting a response from it. But in fact, it's so conducting that there was no secondary field that they're able to sense. And then the Eastern Deeps was found by Magnetotellurics because of this this orange blob here. Here's some work I got from Joel Jensen from Chile, the Santa Cecilia deposit. And the initial work was a very shallow AMT survey in 2010. And that was drilled and then followed up by a deeper MT survey that found this very deep conductor that was the feeder to all these shallow deposits. And this returned economic mineralization. Close to you, just up in the Copper Belt, this slide is originally from Chris Wins, but I got it from Joel Jensen. And here we're not mapping the bodies directly, but we're mapping the geometries. We're mapping these domes, the structural domes in the region. And then one deposit up in the northern Yukon, and this slide, oh, it's hidden under there. This is the Casino deposit. Here you can see the deposit outline, and here are models at different depths above mean sea level through that deposit. There's the deposit outline. You can see these conductors and how they change with depth. So, in conclusion, I hope I've convinced you that Magnetotellurics can be a very cost-effective exploration tool at all scales, from the regional scale using these long period systems to the camp scale to the deposit scale. I have to tell you, it's not an easy technique. No EM method is easy. It's at the scary end of geophysics. You know, you go from potential fields, gravity and magnetics, and then you go to seismics, which is already a bit scary, and then you go to EM, and EM is really the scary end. So you really need deep understanding of the method, and particularly its potential pitfalls. I did a job for a client a year ago. They had some MT done, and based on the MT, they were going to start a $5 million drilling program. And they asked me to look at the data before they did the program. And I looked at the data, and I tore that data every which way. And I could not find the anomaly that they were going to drill. And I found some problems with the data. And so, you know, there's a lot of people doing MT, and not all of them know 100% what they're doing. There's a huge value in revisiting legacy MT data using newer tools. And in fact, my company is getting a lot of work this year because it's a year where companies are not doing new acquisition. And so they're giving us their legacy MT data to look at with our newer tools. And the one thing that's not done, and in fact should be done, once the geophysics is done, we tend to get kicked out of the camp, and then the people come in, and then the drillers come in. But every single borehole gives you crucial information that you can go back and remodel the data with stronger constraints. And that can give you higher resolution structures. And all you need is to cut the cost of one borehole, and you've paid for all this revisiting modeling exercise. So if you want more information, buy my book or contact me. And I'd just like to conclude by thanking particularly my supervisor, Rosemary Hutton, absolutely wonderful woman, actually. And my colleague Bruce Hobbs and I, we've just published a paper in a special issue of the Geological Society that's dedicated to pioneering female geoscientists, and we have a paper on Rosemary Hutton, and when it's out, I implore you to read it, because you'll read. She spent a lot of her life in Africa and did some wonderful work in the 10 years she was in Africa before she moved to Edinburgh. And then I've got a load of other colleagues, and I just threw these names down before I started this webinar, so I'm sure I've forgotten a lot of people out there who are have been hugely important and beneficial to my career. So thank you all for listening, and yeah, I'll be very pleased if anyone's still there to take questions from you.
Thank you very much, Alan, for that. That was extremely comprehensive. I'm sure we have some questions and comments. There are a couple on the chat function. One of them was the success rate. What is the success rate of mineral discoveries using magnetotellurics? Can you throw some light on that?
Success rate of mineral discoveries using MT. Wow. The problem with answering that question is just the confidentiality. Like my company, we're a small player. We've only just started, and there's a number of big players in the game who are doing acquisition. And I know some of these are on their websites. You know, if you go on the website of Applied Geophysics in Toronto, you'll see some examples, because some of their clients allow them to put their examples on. But no, that I'm afraid I can't answer that. I really can't answer that question, because there's just too much that's confidential. I do know that MT has been very successful in parts of Canada. You know, the Voisey's Bay, I just showed you the Eastern Deeps. In Sudbury, looking for deeper deposits over in the Athabasca Basin, for example, a number of areas that I'm familiar with in Canada. But as a general number, for example, X% success rate, I can't give you that. Sorry about that.
There is another question here from Ray Durheim.
Yeah, I'm reading it.
Okay,
Yeah.
it's a pretty specific question.
Yeah.
Can you respond to it?
Yeah, thanks, Ray. You might remember the paper I gave in 1986, one of the seismic reflection meetings that was in Cambridge, and it was called MT and Reflection, an Essential Combination. There's been quite many examples where MT and reflection where the reflection geometry has been used to guide the MT. And in fact, Mike Berry, formerly of physics branch GSC, I remember his phrase was that magnetotellurics paints the layers defined by seismic reflection. I did publish a nice paper. I thought it was a nice paper. I'm getting a bit like Donald Trump now. I should call it a beautiful paper. It was a beautiful paper. I did publish a paper with Fred Cook some years ago, where we looked in intricate detail of the seismic reflection and the MT results on one particular line. And we thought that was very conclusive. And there's a nice piece of work done by Guy Marquis, who was a student of Roy Hyman, that was published in the late 80s, where he actually used one problem with reflection, of course, is you often don't use true amplitude processing, but he took some seismic reflection data and he used true amplitude processing on it. And so we were able to really look at the correspondence between the MT results and true amplitude processed seismic results. But so in terms of integration, yeah, and there's a what we don't have is joint inversion with with seismic reflection information. We have a number of cases. My former student, Max Moorkamp, who appears here, he's got code where he joint inverts travel time data with MT and with gravity, and he's working on refraction data. Joint inversion with reflection data may be a bit tricky. But certainly, I think the point is that there's only one Earth, and we all observe this Earth with polarized spectacles, right? We've got our own technique, our own way of looking at the Earth, and there's no question that the best way to reduce model space is to look at it with all our different techniques, and to try and find a model that's consistent with the gravity and the magnetics and the seismics and the electromagnetics, whichever method you use. And that is our best way of getting of reducing model space, is to do some sort of formal integration of them all.
Can I open the floor to some questions? Just unmute your microphone or raise your hand. Are there any questions or comments? There's still one or two more in the chat box, but I think we'll go to the delegate list now for questions or comments.
Somebody's asking, is there any harm if we go for 2D inversion of 1D data? No, there's no push, Shadhari. There's no harm at all. I don't know why you do it. I mean, the advantage of 1D, the lower the dimension, you know, we have 1D techniques, we have 2D techniques, we have 3D techniques. The lower the dimension, the better tools we have, the better resolution we have, because we can finally discretize the Earth in 1D. In 2D, yes, you could have a 200 by 100 cell size, but then you know, understanding resolution is very difficult, and non-uniqueness. And then when you get to 3D, 3D is so expensive, and I would say we're only at the beginnings of 3D really. 3D is so expensive, it can cost you days on a cluster to get your model, to get one model, that you're just happy with that one model, that you don't go and find other models. And so I would say, try and find the lowest dimension you can. One advantage of going to 2D with 1D to control static shift problems in your MT data. Now this is getting a bit technical, and perhaps most of the audience isn't interested, but once you go to 2D, then you've got a better handle of controlling random shifts of your apparent resistivity curves.
Okay, anybody else? There's still a couple of questions in the chat box. There's Alan, just a general question from me, maybe backing up a little bit and going back to the days of the CapBall program and so forth. In the last few years, are there any advances in or better understanding of cratonic margins and cratonic structures, comparing MT with seismics, for example? Are we still learning things in those areas?
Oh, very much so, Craig. Very much so. I think the excuse me. The problem is that we're doing quite well now because of these national surveys like OSLAMP, and in Australia, of course, you've got an equivalent sort of program for teleseismic acquisition. In the US, you have US Array with both MT and seismics. In China, you have the Sinopro program, which is covering China with MT and teleseismics. And at the moment, I would say that all of us, we're a bit data overwhelmed in our own techniques. And so what you've seen coming out of Australia, for example, we've seen some absolutely fabulous models coming out of the MT groups there, particularly the Adelaide groups and Mike Dentith over in Perth. But we're not seeing how that relates to the teleseismic, because they've not got time, because we have an expression in Canada, I don't know whether you have the same one in South Africa, of drinking from a fire hose. You know, basically just the data is just rolling in so hard that they're having trouble keeping up for it. And you need to have time. I mean, in the Samtex program, we had to get through the MT data before we could stand back and then bring in the seismics. You know, and so we're at the stage, Craig, I would say that over the next 5 to 10 years, because of all these data sets, and when each technique has done its own job on its own data, then we can start to look more closely at these broader questions that you're raising.
This sounds like several PhD programs that could be
certainly,
done during
yeah.
lockdown.
Yeah, you know, the problem is that the way we train our students is not really very conducive to what we need from a modern geoscientist. We need a modern geoscientist to be familiar with a lot of different techniques, and yet most professors still train students to be clones of themselves. And so we have to break out from that paradigm and move to a new paradigm, perhaps where students are jointly supervised by 2 or 3 professors simultaneously, and getting a lot more influence. And the student doesn't just finish a PhD knowing one thing very well, but knows a lot of different things, perhaps not each as well as one, but knows. My view is the challenges are at the boundaries between these disciplines now. We've gone very far in our own individual techniques, be it magnetotellurics, be it seismics, and I think the MT technique has shown itself, and we've taken this a long way. But now the challenge is right on the boundaries, trying to understand the geochemistry, the geophysics, at the boundaries between those different observables.
Okay, thank you, Alan. Are there any other questions from the audience?
Hello. Good evening, sir.
Yeah.
Sir, my question is something about the geoelectric strike. When we go to for geoelectric strike, either we got 0 to 90 degree its value, or vary from 0 to minus 90 degree, depending upon the geology. Why we go in these 2 domain, minus 90 to 90? Why go further 180, something like that? Is there any mathematical issue?
Yeah, so, you know, your question is of a highly technical nature that's not going to be of interest to most of the people listening to this. Can I ask you to send me an email, and I'll reply directly to you on that question? I think for the benefit of most of the audience, I'd rather that the questions stay more general than so technical about magnetotellurics.
Some of us are mere geologists.
Hey, listen, I hate to say this, but I've had one course in geology all my life, and that was during my master's in Birmingham. And I need to, when I was at the Geological Survey of Canada, I loved working there because I used to be able to wander into the offices of some of my favorite geologists and get a lot of information. So there's no such thing as just geologists, you know, we're all in this together.
There was one other question on the chat box concerning the use of MT on the seafloor.
Yeah, I didn't mention the seafloor because I didn't think there'd be a lot of interest in the audience on the seafloor, but there is a huge amount done on the seafloor, both on the deep sea floor and on the shelf. What was the nature of the question? how is this done? Is there anything special? Oh, there's a lot of special things that have to be done. They use special electrodes, silver nitrate electrodes. They they have to put the instruments in cases. They have to send them down, and then they have to get them back up. It's a very different game, and it's, in terms of cost, I would at least an order of magnitude more expensive. At least an order of magnitude more expensive per site than standard MT, if not more. And yeah, there's perhaps the for the seafloor, the control source methods are of more value at this time, because there's where you put down sensors and you can tow a source, or you can put down a source and tow sensors, and you can get information about the shallow part. So you can look for offshore minerals, extractable offshore minerals in the shelf.
Okay, there's still a couple questions in the chat box, but I think I'm going to cut the discussion here. You're welcome to email Alan, I'm sure.
Yeah,
with
please
any of these
do. Please
questions,
do.
and he'll
Yeah.
come back to you.
Yeah.
Is there anything else from the floor? Going once, going twice.
Thank you, everybody. And as Craig says, yeah.
Thank you very much, and thank you to TerraCore Geospectral Imaging for sponsoring the July lectures in the lockdown series. But Alan, thanks very much for agreeing to participate, and we'll see you again at some stage, I'm sure.
Thank you very much, everyone. Thanks. Please do send questions. And I do hope I hit it right, you know, because I couldn't see your reactions. So I do hope I didn't lose too many of you in technical jargon. Thanks very much, everyone, for listening in.
Thanks, Alan, for joining us.
Okay. Right, bye.
Bye.
Bye. I'll end the meeting now.